This is a quick video over the Nusselt number. Now the Nusselt number is actually a ratio. It is and it's usually written as NU, and it is the ratio of heat transferred, so Q dot due to convection, over Q dot conduction. And remember, Q convection is due to maybe fluid flowing past. Let's say you had a ball and it was some temperature, and you started flowing a fluid across the ball. And the fluid would be some temperature T1 and the ball is some temperature T2. And as the water flows past, it would pick up some of the heat and transfer it away from the ball. That's convection. And conduction is when you have a block that's some temperature T1 and you put it next to another block that's another temperature T2. Now there's no moving parts, it's just the heat diffuses across or into, or however you wish to think of heat movement. It crosses into it, but none of the atoms or anything are moving. It's just they're stationary, and the only thing that is transferring is heat. So how do you calculate Q convection? So Q dot convection. It is equal to H times delta T. And remember, H is the convection heat transfer coefficient. Convection heat transfer unit. And it varies from liquid to liquid and how fast that liquid's moving. But the units of H are watts per meter squared degrees Celsius. So now we have what Q convection is. What's Q conduction? Q conduction. It is equal to K times the change in temperature over the length. And K is dependent on what the material is. So if it's water, it has its own. If it's steel, it's different. And metals tend to have very high K values versus gases are maybe just like insulation tend to have very low K values. So let's say you had two boxes. This one's at T1, and instead of having them right next to each other, let's put another box right between them. And this is T2. The length that we discuss is this length. So if we were to make this longer, the heat transferred across would be less. And that is conduction. It's just heat transfer. There's no molecular movement across anything. The molecules or ions or whatever they may be, they're still in the, or not ions, but they're still in the exact same area. Or yeah, ions too. So they're still in the same area. So if we were to combine these into the ratio that we said what the Nusselt number was, which was right here, if we were to do that, we said that the Nusselt number is equal to the Q convection over Q dot conduction. So if we put this in for Q convection, we get H times delta T over with putting in now this for Q conduction, K times delta T over L. And what we see is the delta L's cancel, and this flips up over here. So what we get is the Nusselt number is equal to H times L over K. And remember, this L, that L represents this a length of something like this. That is the Nusselt number at its most basic. There are a ton of equations that you can use to calculate the Nusselt number, but the concept is Q convection over Q conduction. So maybe let's say you had maybe something like a heavy oil. The convection by that heavy oil would be relatively low. Most of the heat transfer from the item to the oil would be due to conduction. So if we had maybe a tube and we tried flowing some heavy oil, very heavy oil, it would be laminar, and we'd see that it would be something like this. So this is a laminar. So we do have our fluid flowing through, but again, due to the viscosity of this, you wouldn't really get these convective forces like you would for water, where the water may be turbulent and it's just flowing around all over the place. It's getting eddies generated, so it's mixing really well. And with water, you'd have a very high convection and maybe a low conduction. So the Nusselt number represents how the heat transfers. So if you have a high Nusselt number, that means you have a high convective force, or heat transfer due to convection versus heat transfer due to conduction. Or if you have a low Nusselt number, that means you have very little heat convection and a lot of heat conduction. That is a Nusselt number at its most basic.